Welcome to this GeoStudio Material Model webinar series on the hardening soil model. My name is Curtis Keln. I'm the Director of Research and Development with the GeoSlope Engineering team at Sequent. Today's webinar will be approximately 30 minutes long. Attendees can ask questions using the chat feature, and I will respond to these questions by email as quickly as possible. A recording of the webinar will be available so that you can review the demonstration at a later time. GeoStudio was developed for geotechnical engineers and earth scientists. As such, it comprises a range of products that can be used independently or together to solve a wide array of problems. Today's webinar will focus on Sigma W. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoSlope website. Here you can find tutorial videos, examples with detailed explanations, and reference books on heat and mass transfer modeling, static stress strain modeling, slope stability modeling, and dynamic stress strain modeling with GeoStudio. To begin this webinar, let us consider a soil specimen subject to an experimental procedure and a numerical simulation of that experimental procedure. In an experimental approach, there's a real soil sample from which specimens can be extracted and subjected to various tests, such as triaxial and odometer loading. The data collected from these tests is then interpreted, and the interpretation has to be done in a manner that is specific to a particular constitutive model. The parameterization procedure produces the model's constants. These constants are then used as inputs for the model. The simulated results are obtained by solving the physics subject to boundary conditions and a constitutive law. And finally, the simulated results are compared to the corresponding laboratory results to verify the parameterization. In today's webinar, we will review the key elements of the hardening soil constitutive model. Then, a step-by-step procedure will be presented for parameterizing the model. The procedure will then be applied to data from numerous triaxial tests on sandy soil. A demonstration of the steps for modeling a triaxial test in Sigma will be provided, and the simulated and measured results will be compared. Some concluding remarks will also be provided at the end of the webinar. The hardening soil model was proposed by Shans, Vermeer, and Bonnier in 1999. It was formulated on the framework of the classical theory of plasticity. The formulation comprises 3 stress-dependent stiffness quantities and 2 yield surfaces, one that resembles a hexagonal cone and a second that resembles the tip of an ellipsoid. The shear surface predominantly governs the response to changes in deviatoric stress, while the cap predominantly governs the response to increments in mean effective stress. Failure is controlled by a Moore-Coulomb failure law, hence the hexagonal shape of the yield surface. The model implemented in Sigma actually comprises a smoother cap than what is depicted in this figure. The reference book should be consulted to understand the details of the formulation. In a triaxial stress state, the total stress path is a straight line that reaches the Moore-Coulomb envelope at a specific failure point. The deviatoric stress axial strain response of the soil under this loading condition is estimated by a hyperbolic curve. As will be discussed shortly, the characteristics of this curve are determined by 3 stress-dependent stiffness quantities, including the initial tangent stiffness, E subscript I, the half-failure secant stiffness, E subscript 50, and an unloading-reloading stiffness, E subscript UR. In order to have a closed yield surface, a cap function is defined in the hardening soil model. This cap has an elliptical shape with an aspect ratio of m, or the Greek letter mu. In the PQ stress space, the stress state of any normally consolidated sample, is located on the cap. That's at the tip of this blue stress path that intersects the ellipse. The stress-strain behavior of the sample in an odometer test is defined by a tangent stiffness called the odometer stiffness, or E subscript OED. Like the other stiffness quantities, the odometer stiffness is not constant, but its value depends on the stress of the specimen. To review the key ingredients of the hardening soil model, let's consider a theoretical triaxial response. The axial strain of the sample in this condition is defined by a hyperbolic function. The hyperbolic curve continues until the Moore-Coulomb failure stress is reached, Q subscript F. The failure occurs before the curve reaches its asymptotic value. The ratio of the failure to asymptotic deviatoric stresses is R subscript F. The behavior of the sample at the beginning of loading is modeled by the initial stiffness, E subscript I. Since this quantity is difficult to measure, its value is presented in terms of the half-failure secant stiffness, E subscript 50. The half-failure secant stiffness is a stress-dependent stiffness that depends on the minimum principal stress, sigma subscript 3. A similar stress dependency is also considered in the hardening soil model for unloading-reloading stiffness. The model's constants are now highlighted in gray. In an odometer test on normally consolidated soil, the slope of the stress path is a function of the coefficient of lateral earth pressure, K0, superscript, NC. Moreover, the cap yield surface in PQ space is an ellipse with a horizontal major axis. In a non-cohesive soil, the elliptical yield surface is centered around the origin. The odometer stiffness is also a stress-dependent stiffness, presented in terms of the vertical stress sigma 1 in a one-dimensional odometer test. Notice that the dependence on sigma 1 is different from the other moduli that were dependent on sigma 3. The model's constants are once again highlighted in light gray. To summarize, the hardening soil model requires 3 stiffness constants, a reference stress, and an exponent m. The strength constants and failure ratio are subscript F, the coefficient of lateral earth pressure. Some other parameters will also be needed to describe the initial condition of a specific soil sample. These include the initial void ratio, the unit weight of the soil, and an isotropic overconsolidation ratio, which we'll touch on briefly in the subsequent slides. We can now discuss a step-by-step parameterization procedure for determining the hardening soil model constants from a number of drain triaxial tests. Step 1 involves determination of the effective friction angle and the effective cohesion C. The failure stress from numerous triaxial tests at different confining pressures are theoretically located on the Moore-Coulomb failure line in PQ space. As such, the slope of the line, which is tan beta, as well as the y-intercept, alpha, is calculated using the method of least squares, where n is the number of data points. Alternatively, the trendline functionality in programs like Excel can be used instead of the least squares formulas. The effective friction angle and effective cohesion of the soil can be found by changing the coordinate system to a shear normal stress space. The equations corresponding to that transformation are shown here. The second step of the procedure is to consider a reference stress and to estimate reference stiffnesses. One of the available triaxial tests is considered as a reference test. The confining pressure of this test is then called the reference stress. The failure deviatoric stress for this particular test is determined based on the Moore-Coulomb strength constants determined in the previous step. The half-failure reference stiffness is the slope of a straight line that passes through the point carrying 50% of the failure deviatoric stress. The least squared methods is applied again on the unloading-reloading branch of the stress-strain curve to calculate E subscript UR. In the third step of the procedure, the stress dependency exponent M is estimated. In stress-strain curves of drain triaxial tests with different confining pressures, half-failure stresses are first calculated using the method described in step 2. A new natural log space can then be defined that represents the half-failure stiffnesses of each test in the form of a single point. The point corresponding to the reference test is located on the origin. The stress dependency exponent M is the slope of a trend line that passes through these points. The similar steps can be taken for unloading-reloading in order to calculate the stress dependency exponent twice. In the hardening soil model, however, it is assumed that the constant M is the same for both half-failure and unloading-reloading stiffnesses. The fourth step of the parameterization procedure is to calculate the failure ratio RF. This constant has a value between 0.5 and 1, and is usually assumed to be 0.9. A more accurate value for this constant can be calculated based on the results of the triaxial tests. First, the stress-strain hyperbolic function is rewritten in terms of the failure ratio R subscript F. This expression introduces a new coordinate system in which each hyperbolic curve is projected to a straight line. The failure ratio is the slope of these parallel lines. In the second last step of the parameterization procedure, the odometer reference stiffness and the coefficient of lateral earth pressure are estimated. The odometer test result is required for this step. However, these values can be approximated in the case where the appropriate laboratory result is not available. As mentioned earlier, the odometer reference stiffness is defined in a one-dimensional compression test. By definition, it is the tangent stiffness at the point where the vertical stress is equal to the reference stress. In addition, the coefficient of lateral earth pressure for a normally consolidated soil, K0 NC, is the ratio of lateral stress, sigma 3, to vertical stress, sigma 1, in the odometer test. These two constants must be approximated in the absence of laboratory data. For instance, the value of the odometer reference stiffness is usually greater than 50% of E50 ref and less than 80% of E50 ref. And also, the coefficient of lateral earth pressure can be estimated using the well-known Jakey's formula, which relies on the friction angle of the soil. One additional step in the parameterization procedure is required if the soil is overconsolidated, and that is the determination of the isotropic overconsolidation ratio, which is a ratio of equivalent isotropic stresses. The denominator of this expression is simply the confining pressure of the triaxial test. In contrast, the numerator, P subscript C, defines the size of the yield locus passing through the yield stresses Qy and Py. As such, P subscript C must be calculated from the equation of the yield function. The yield stresses are generally determined from plots of deviatoric stress versus axial strain and void ratio versus natural log mean effective stress, and in both of these plots, the yield point, that is, that transition from elastic to elastic plastic behavior, is deduced by an inflection point in the measured laboratory data. That brings us to the constant mu, which is in the equation for the cap yield function. It is calculated by the material model in the solver from this expression here. We elaborate on this expression in the reference book, but for the purpose of this webinar, it suffices to say that eta is a Q over P stress ratio that can be calculated from the user input K naught and C, which we discussed on the previous slide, and lambda over kappa is calculated from Poisson's ratio and this ratio of reference stiffnesses. Now, the entire procedure for determining OCR can be simplified if the stress path is instead that of isotropic compression, because in that case, the stress path tracks along the mean effective stress axes, meaning that the deviatoric stress is 0 and PC is equal to Py. To demonstrate the parameterization procedure, we are going to consider 12 drain triaxial compression tests on Ottawa sand. These tests were performed at different confining pressures ranging from 50 to 600 kilopascals. The effective friction angle and the cohesion of the soil are calculated from the first step of the parameterization procedure. The deviatoric compression stress in 12 triaxial tests continued until failure was achieved. The failure state of each test can be represented by a point in PQ space. The failure line that passes through these failure points has a slope of 1.18 and a y-intercept of 0. Therefore, the effective friction angle is calculated as 29.6 degrees, while the cohesion is calculated as 0 since alpha is 0. At the second step of the procedure, the test with the confining stress of 100 kPa is considered as the reference test. The half-failure deviatoric stress for this reference test is calculated to be 97.6 kilopascals. According to the measured stress strain curve, the axial strain corresponding to this half-failure stress is equal to 0.0055. This means that the half-failure reference stiffness for the soil is 17,745 kilopascals. Again, that is simply the slope of this line. Finally, the unloading-reloading branch of the measured stress strain curve gives us the value of the unloading-reloading reference stiffness, and the slope of that line is estimated to be 45,000 kilopascals. The third step of the parameterization procedure estimates the stress dependency exponent m. As shown here, this constant can be estimated from either the unloading-reloading or the half-failure stiffnesses in natural log space. The slope of these two lines is almost the same, and their average is 0.680, and this is what we consider to be the constant m. As can be seen here, the proposed expressions can adequately estimate the unloading-reloading and half-failure stiffnesses in terms of their corresponding confining stress, sigma 3. The proposed curve, however, is more consistent with the measured results for the unloading-reloading stiffnesses than for the half-failure stiffnesses. This is commonly the case. The failure ratio R subscript F is calculated at the fourth step. The linear projections of the hyperbolic curves are shown in the suggested space in the left graph. The near vertical branches of these curves represent unloading-reloading phases where Q approaches 0, causing the ratio of QF over Q to approach infinity. These near vertical branches are not included in the calculation of RF. Rather, it is the sloping portions of the curves that are described by the equation of a line, where the slope of each line is R subscript F. The graph on the right shows these slopes for all 12 triaxial tests. The average of 0.941 is then estimated for the failure ratio of this soil. For the odometer-related constants at step 5, we apply the approximate method of calculating the odometer reference stiffness. According to the value of the half-failure reference stiffness, which was calculated at the second step, we estimate the odometer reference stiffness to be 11,500 kilopascals. The Jakey's formula is also used to calculate the coefficient of lateral earth pressure in terms of the effective friction angle, and from that relationship we obtain 0.506. The results of the parameterization procedure for the Ottawa sand can be summarized as follows. Our two strength constants gave us a friction angle of 29.6 and a cohesion of 0. The reference stress was 100 kilopascals and the reference stiffnesses were calculated accordingly. The stress dependency exponent and the failure ratio were estimated as 0.68 and 0.941 respectively, and the coefficient of lateral earth pressure was obtained from Jakey's formula to be 0.506. Now that we have reviewed the step-by-step parameterization procedure for the hardening soil model, I will describe how to model a triaxial test in Sigma and compare the numerical results with the previously mentioned lab data. The numerical model configuration is based on the geometry and boundary conditions of the triaxial test conducted in the laboratory. A typical triaxial sample has a cylindrical shape with a diameter of 5 centimeters and a height of 10 centimeters. Due to axisymmetric shape of this geometry with respect to the central vertical axis, we use a 2D axisymmetric geometry in Sigma. The geometry is also symmetric with respect to the horizontal axes, so we can model the top 1/4 of the specimen. An 8-node single-element model is considered for this resulting rectangle. The material definition is, of course, the key subject of this webinar. This step is performed in the software using the Define Materials dialog box. The material model is set to the hardening soil model. The sample parameters, including the initial void ratio and overconsolidation ratio, are entered. It should be noted that the effect of the soil self-weight can be removed by setting the unit weight to 0. And lastly, the constitutive model constants are entered based on what was previously obtained during the parameterization procedure for the Ottawa sand. The triaxial tests are simulated by firstly considering the isotropic confining pressure, and secondly, the deviatoric pressure. To do this, the project file is set up with an analysis tree structure for each test. In each branch, we see the confining pressure phase acting as a parent, which provides initial data to the subsequent displacement controlled deviatoric phase. In test A1, as an example, a constant normal stress of 50 kPa is applied on both the right and top sides of the model using a normal tangential stress boundary condition. And in the deviatoric phase of this test, a displacement of 2 centimeters, that is equivalent to 40% strain, is applied on the top side of the model. The displacement spline data function contains a small blip at just before an elapsed time of 1.2, and this is the unloading-reloading phase. Let's just take a few minutes to explore some of the finer details of these ostensibly simple numerical analyses. First, we'll start at the top of the project definition, and I will point out that you can right-click on here and add multiple geometries to the same project file. In this analysis, of course, we have only one single geometry, and it is of the type 2D axisymmetric. The next noteworthy thing under our geometry sits our confining stress analyses for all 12 triaxial tests. And then, unlike what is shown in the PowerPoint presentation, we actually have two cases for each deviatoric loading condition. one that is monotonic, meaning strained without unload reload, and the other with the LUR, or load unload reload branch. All three of the analyses in each branch are load deformation. Now the first analysis is the one in which we apply the confining pressure of 50 all the way through to 600 kilopascals. And it is an analysis of the type load deformation. We're not doing an in situ or gravity activation analysis because the dimensions of the specimen are so negligible that the body load or the gravity load doesn't contribute to the stresses in any meaningful way. The other thing that's worth noting is that our deviatoric phases are also load deformation, and the initial stresses and pore pressures come from the parent analysis. We also have the ability to set the final pore water pressure conditions, and you can see in this case it's the same as the initial conditions, meaning that there's no increment or decrement in the pore water pressure. Had these been different, due to, for example, specifying the pore pressures from another GeoStudio analysis like sigma or SEEP, or the use of a water table or a spatial function to define the pressure heads, then that change in pore water pressure would be reflected in the deformation response, the simulated deformation response of the specimen. I should also note while I'm here that there are these two options to reset displacements and strains and reset state variables. These are not on automatically when a load deformation analysis is added to another load deformation analysis. And so they were not set in this case. Now that means that any of the deformations accumulated during the isotropic compression will carry through into the deviatoric loading phase. And so in actuality, it would have been better modeling practice to toggle the reset displacements and strains, and these are accumulated values, to toggle that on. If you're using a material model that has state, like the hardening soil model, in the confining phase, then you can also reset the state variables. Now in this case, what we've done is we've used an isotropic elastic material model in the compression phase, and we've given it a very high stiffness quantity of 50 million kilopascals, meaning that the simulated deformations from this phase are negligible, and therefore we need not reset the accumulated displacements and strains. The other point I'll make is that when you deal with large project files containing multiple analyses, there are right-click options in the Solve Manager to uncheck all, to check children, which picks a single branch, that's the A01 branch, and then there are a couple other options. Similarly, if you go up into the Solve Manager, it's often more convenient if these branches are quite elaborate. In this case, there are only two analyses that are parented to the confining stress analysis, but we can imagine a scenario where there are 8, 12, and so on analyses underneath the parent analysis, in which case right-clicking up here and queuing an analysis branch for solving is more convenient. You can also, in queuing, you can clear, and you can also queue one particular analysis. Now in this case, I'm going to right-click and check all analyses, and then solve. And once the solution is obtained for any one of these, we can switch to the results view. And it is here where we can go to Draw Graph and consider the response through various graphs, such as deviatoric stress versus axial strain, deviatoric stress versus mean effective stress, and void ratio versus P. You can see that there's an unload branch in there. There's the monotonic loading case. You can also multi-select these graphs, which of course gives a rather strange view since the axes are not all the same, but I just wanted to point out that you can copy this graph data and then go to a spreadsheet program like Excel, where you can then right-click and paste the data into the spreadsheet. This will then make for easier comparison with the measured laboratory data. Let's return now to the PowerPoint presentation. The simulation results of 6 triaxial tests with confining pressures ranging from 50 to 300 kilopascals are compared here with laboratory results. Colored curves are laboratory results, and the black lines are the results from the sigma simulation. An analytical solution is also shown on these plots as gray dashed lines. The full compatibility of the analytical and simulated solutions verifies the implementation of the hardening soil model in sigma W. In addition, the acceptable consistency between the lab data and the simulated response confirms that the hardening soil model, with carefully parameterized material constants, can capture the stress-strain response of the Ottawa sand. The same trends can be observed for the next 6 tests that had confining pressures ranging from 350 kilopascals to 600 kilopascals. To conclude, the parameterization procedure of the hardening soil model was provided in 5 straightforward steps and a 6th optional step for over-consolidated soil. It was shown that the results from multiple drain triaxial tests and at least one odometer test are required to parameterize the hardening soil model. In the absence of odometer data, approximations can be used to obtain the reference odometer stiffness and the K0 NC or normally compressed earth pressure coefficient inputs. The material constants were then used in numerical simulations of the lab tests, and the numerical results were shown to compare favorably with both the laboratory data and analytical solutions. During the presentation, I referenced these top 2 articles, Shands, Vermeer, and Bonnier. That's the original model formulation. I also want to remind you that you can consult our stress-strain modeling with GeoStudio 2021 reference book to understand the details of the formulation. And then this is the paper that comprises the laboratory tests on the Ottawa sand. I'll also remind you that the website comprises a number of resources, including example files. One noteworthy example is that of the tieback wall in Berlin. It is completed using both the Moore-Coulomb and hardening soil models, and those results are compared. With that, we've reached the end of the webinar. A recording will be available to view online. Please take time to complete the short survey that appears on your screen so that we know the types of webinars that are of interest to you. Thank you very much for joining us.